All right, so today we're going to first discuss the solutions for the midterm exam. And I will return the graded paper next week, okay? All right, so the first question is about degree sequence, okay? So the first one, you're given a graph, it's G1, and the first question is the number of components of this graph, okay? So clearly there are two components here, okay? So the first answer is 2, okay? And the second question is about this 3, 3, 3, 3, 2, 1, 1 degree sequence. Is it graphical, okay? And the answer is yes, because this graph, G1, realizes this degree sequence, okay? So the second answer is yes, and the reason is G1 realizes the degree sequence. And the third question is, so is this degree sequence potentially connected, okay? So potentially connected means there's a kinetic graph that can realize the degree sequence, okay? So for G1, it is not connected, but we can slightly adjust the graph. Okay, so this is G1, okay? So we've discussed an algorithm to transform a disconnected graph into a connected one with the same degree sequence. So the basic idea is to find an edge such that this edge, even if this edge is removed, the component is still connected, okay? So for example, for this component, we can choose any edge from this component, because no matter which edge you choose, after you remove it from the component, it is still connected, okay? And we choose another edge from a different component, and then we just remove these two edges and add new edges between the two two pairs of endpoints, okay? So we get a kinetic graph, and the degree sequence stays the same. So this degree sequence is potentially connected, okay? And the last one is this one, a bipartite graph, okay? So the answer is no, because there's a triangle, okay? So for this component, you can find a triangle, and a triangle is just an arc cycle. If you have an arc cycle in the graph, then the graph cannot be a bipartite graph, okay? So the answer is no, because the graph contains arc cycle. So the second question, okay, so there are 8 numbers in the degree sequence, so we just create 8 vertices, okay? And we want to add some edges to these vertices so that the degree sequence matches this input degree sequence, okay? So yeah, I think this is quite straightforward, okay? So you just pick any vertex, okay? For example, this one, and add edges to the vertex. And the other endpoint must be the vertices with the highest degrees, or highest like target degrees, okay? So since the degree is 5, you need to add 5 edges, okay? And these edges must be connected to the other vertices that have the largest degrees. Okay, and then we just update the remaining degrees, okay? And so the remaining degrees are 2, 2, 2, and 4 1s, okay? So whenever you see whenever you see multiple 2s, okay, so here we have 3, we can just use a cycle, okay, to connect all these vertices whose target degrees are 2, okay? So yeah, in this way, every vertex receives exactly 2 edges, okay? And whenever you see a bunch of 1s, you can just add like a matching to these vertices, okay? Yeah, so the degree sequence is graphical, okay? Okay. So the next question is, well, to design an algorithm, okay? So the input to this algorithm is age-weighted bipartite graph. So actually, you can change this to any graph, okay? Not necessarily bipartite graph, okay? So it can contain art cycle. That's okay, okay? But anyway, let's assume that this is a bipartite graph and these edges have weights. And the output, first of all, it has a constraint that the output must be the maximum coordinated matching. In other words, it must have the highest number of edges in the matching, okay? And so you can have multiple maximum coordinated matchings, okay? There may be 2 or 3 or even more matchings. They all have the same number of edges, and the number of edges is maximized, okay? So among these maximum coordinated matchings, I want to find the one that has the largest total edge weight, okay? So for example, okay, suppose this is the input, okay? So this is a bipartite graph, and edges have weights, okay? So if you want to have the maximum weighted matching, then you will just pick this edge, okay? The one that has weight 100. This will maximize the total edge weight, okay? But this is not what we're looking for, okay? We want to find, first of all, it must be a maximum coordinated matching. That is, it must have the most number of edges, okay? So in this input, we can only choose these 2 edges, okay? Because this one has the largest size, okay? Yeah, so this problem is not exactly maximum weighted matching, in the sense that sometimes maximum weighted matching may be, like smaller than maximum coordinated matching. Okay, so it is not necessarily a maximum weighted matching. Okay. Now, among all the maximum coordinated matching, we want to have the highest total edge weight. Okay. Okay. So the algorithm is quite simple. Okay. So first of all, we want to make sure that the output is a maximum coordinated matching. Okay? So what we'll do is we will add a very large weight to these edge weights. Okay? So for example, let's add, say 1,000. Okay? So next I'm going to add this 1,000 to every edge. Okay? And then I just output the maximum weighted matching. Okay? So this W is a very large number. Okay? So for example, W can be the total edge weight of the graph. So in this case, you can set W to 1 plus 100 plus 1. Okay? Okay? And the second step is to output the maximum weighted matching. And this is with respect to the new edge weight. Okay? So the intuition behind this algorithm is that after you add a very large number to every edge weight, if you want to find the maximum weighted matching, you need to choose as many edges as possible. Okay? By maximizing the number of edges, naturally you increase the total edge weight. Okay? So this is the first intuition. And the second intuition is that for every edge, for every matching, the new weight is equal to the old weight plus the number of edges in the matching times m. Okay, so for example, here we have 2 edges. Okay, so what is the new weight? So let's consider this matching. So the old weight is just 1 plus 1. Okay, so we choose these 2 edges. Each one has a weight of 1. And the new weight is just let's first compute. Okay, so this one has 1,000 plus 1 plus 1 plus 1,000. Okay, so this is by definition. Okay, we just compute the sum of these edge weights, but this just equals, the old weight plus the size of the matching times 1,000. Okay? So why is this important? The reason that this is important is because whenever you have 2 matchings of the same size, okay, then so if you have 2 matchings, M1 and M2, and they have the same size, then, and let's further assume that the old weight or the original weight of M1 so it's like M1 is heavier than M2 if you consider the original or the old weight. So if this is true, then this is true also for the new weight. Okay, so after you modify the edge weights, you still preserve the relative order between matchings of the same size. Okay, and this is true for the other direction. Okay, so by maximizing the new weight, you also maximizing the original weight, okay? Because, well, you add the same number to every edge, okay? So that's why. OK， 所以这演算法蛮简单的，就是我们会把每一个 edge weight 都加上一个很大的数字。我刚刚没有特别讲这个要多大 ，OK？ 简单说就是要大到我一定会选到最多的 edge，OK？ 所以，譬如说，如果你这边只加个0.1，刚刚是加1000嘛 ，OK？ 如果你这边只加0.1就还不够大 ，OK？ 所以只要够大，大到说，你一定要选最多的 edge， 就会是最好的，那就是够大。那举例来讲，我刚刚说，譬如说你把所有的 edge weight 都加起来，或者是你把最大的 edge weight， 然后再乘上，比如说乘上 n 之类的，这些都可以 ，OK？ 好，然后你把这个数字加到所有的 edge weight 之后，你再去算一个 maximum weighted matching。那这个我们之前也有讲过 ，OK？ 所以事实上考卷最后题就是这个 ，OK？ 所以这个演算法第一个，因为你加的这个 W 是够大了，所以它一定就会 output 一个 maximum cardinality matching，OK？ 然后再来就是后面说的这一个。就是它会类似保留这些 matching 之间相对的大小的关系。我这边的大小指的是 weight，OK？ 所以你去 maximize 新的 weight， 就相当于你去 maximize 旧的 weight。OK？ OK， 所以这一题有问题吗？ Or are there any other possible designs for this question? 我不知道大家有没有写其他的，因为我还没有看大家的答案呢，不确定大家有没有写不一样的做法。OK， 如果没有，我们就往下。So for the next question, we will discuss dominating set. Okay. So a dominating set is, first of all, it's a subset of vertices in a graph, okay? So intuitively, this dominating set, it kind of dominates every vertex in a graph. So how to dominate a vertex? So there are two methods to dominate a vertex. So for example, if I want to dominate V1, then you can, first of all, just choose V1. By choosing V1, you dominate V1. So this is one way. The second way is to choose one of its neighbors, okay? So if you want to dominate V1, then you can choose V4, V5, or V6, okay? So that's a dominating set, okay? So in the problem of minimum dominating set, we want to use the fewest vertices to dominate the whole graph, or the whole vertex set, okay? So this is an NP-hard problem, okay? But anyway, for this question, you only need to write down the mixed integer linear program, okay? Okay. So the first step is to create the variables. So in this minimum dominating set problem, we have to decide for each vertex whether we pick it or not. Okay. So there's a binary variable associated with every vertex. Okay. So for every vertex vi, we create a variable xi. Okay. So in this particular instance, since there are 6 vertices, so we'll create 6 variables. Okay. And the objective is to choose the smallest possible number of vertices, or the fewest vertices. Okay. All right, so since there are 6 variables, we just compute the sum, okay? So we want to minimize the sum, okay? So this sum has the physical meaning of, well, the number of vertices chosen by the, by the algorithm. So we have some constraints. So the constraint is that for every vertex, we have to ensure that the vertex is dominated, okay? So for every vertex, either itself is chosen or its neighbors, one of its neighbors is chosen, okay? So we have a constraint for every vertex. So we start from V1. So to dominate V1, we have to make sure that either V1 is chosen or V4, V5, or V6 is chosen. Okay, so we can express this constraint using this inequality. Okay, and recall that this xi is a binary variable, so it can take value between 0 or 1. Okay. So if it's 0, then it means we do not choose the vertex, okay? And if it is 1, then it means we choose the vertex. So the left-hand side of this inequality is just the number of vertices chosen in this set, okay? The set of V1, V4, V5, and V6. And we want to make sure that at least one of them is chosen. So the constraint says the left-hand side should be at least 1 to make sure that one of the vertices must be chosen. So yeah, we just apply the same idea to every other vertex. So for V2, V2 or V3 or V6 must be chosen. And similarly for V3, okay. And for V4, okay. So these are just the corresponding constraint for every vertex. Okay. And finally, these variables are binary variables. Okay. Okay, so yeah, this is the corresponding mixed integer linear program for this particular instance. Okay, so next we have to find the dual problem. Okay. So to create the dual problem, you first create the dual variables. Okay, so you have one dual variable for every constraint. Okay, and recall that we have one constraint for every vertex. So this means we have one dual variable for every vertex. Okay, and so the objective of the dual problem is to maximize like the inner product of y, that is the dual variable, and the right-hand side. Okay, so it is just the sum of all the dual variables. Okay. Okay, and then we have the constraint. So we have one constraint for every primal variable. Okay. Okay, since we have 6 primal variables, so we have 6 constraints. And the right-hand side of the constraints are just the coefficient of the primal variable in the objective function. So these are just ones. And then we have to figure out the coefficient in the linear combination of these constraints. So first of all, let's find the coefficient for x1. Okay, so the coefficient of x1 contains y1 and y4, y5, and y6. So you can see that the indexes for the first constraint, okay, 1, 4, 5, 6, this matches the indexes here for the dual problem. Okay. So the next one is for the coefficient of x2. Okay. Okay. So I think after the first two constraints, it's easy to see that. So actually, the left-hand side of the constraint, just like the left-hand side of the constraint in the primal problem. The only difference is that we change x to y. Okay. So the same left-hand side, the only difference, we change x to 1. Okay? So this is the dual problem. Okay? All right, so next we have to write down the general mixed integer linear program for the dominating set problem. Okay? Okay, so the basic idea is still the same. We have one variable for every vertex. So we have to express this sum for the general graph. Okay, so let's assume that we have n vertices. Okay, so the sum is just x1 plus x2 up to xn. Okay. So I think this is not the only way to express the objective function. There are different ways of expressing this objective function. Okay, so for example, you can have something like, say, we have a variable xv for every vertex v. Then the objective function will be something like this, okay? So you consider all the vertices in the graph and compute the sum of the corresponding variables. So yeah, so really there are lots of ways to express the objective function. Okay? And the constraint is that for every vertex we have to dominate it. Okay? So for every vertex vi, we have a constraint. And the constraint is xi plus the neighbors of vi. Okay? So this is the left-hand side. And it should be at least 1. Okay? So and finally, all these variables are binary variables. Okay, so if you choose this notation, then you can have constraints like this, okay? And this is for every vertex. Okay, so for every vertex v in the graph G, we have one constraint. Constraint says xv plus the summation consider all the neighbors of v, and that's called u. So this is just, sorry, so this should be xu. Okay. Okay. So this should be at least 1. Okay. Okay. And for the dual problem, according to our previous observation, we know that the objective function is just the sum of all dual variables. And since there are n constraints, we have n dual variables. And since the left-hand side is just, well, it's the same, okay? We just change x to 1. Okay. So that's a dual problem. Okay. So now, what is the physical meaning of this dual problem? Okay. So first of all, what is the objective? Okay. So in this objective, and also we have this non-negative constraint. Okay. So for every vertex here, we have to assign a number, a positive number. Okay, and we want to maximize the sum of these numbers. Okay, so let's go. But in order to maximize these variables, we also have to respect the constraints. So here the constraint is that for V1, the number or the weight of Y1 plus Y4 plus Y5 plus Y6, it cannot be larger than 1. Okay, so it poses an upper bound for these numbers. Okay. Right. So for this question, the physical meaning is just like we have to assign numbers to the vertices, and we have some upper bounds for every vertex and its neighbors. Okay, and the upper bound is just 1. Okay, so for example, you can try something like 0.5 here. Okay, so after we assign 0.5, 0.1, 0.2, when we consider V6, it can be at most 0.2. Yes, you can also pose the constraint that it is also binary. You can also do that. So if you only consider binary variables, then, for example, you set this to 1, then all the other variables must be 0. Yeah, that's also okay. Yeah. Okay, and yeah, so if you consider binary variables, then it's like you want to choose as many vertices as possible. But for every vertex and its neighbors, you can choose at most one of them. This is also a possible interpretation of the dual problem, okay? To maximize the number of vertices that you choose, okay? But for every vertex and its neighbors, you can choose at most one of them. Okay. So yeah, this is also a feasible solution or feasible explanation. All right. So for the last problem, I think the answer is 32. Okay. So I won't go over the process again because it's just the same algorithm, and the answer is 32. Okay. Mm-hmm. Mm-hmm. Let's just consider this example, okay? So first of all, what is your output? Okay. OK，还有其他问题吗？OK, so the problem is the difference between dominating set and vertex cover. So by definition, we have a constraint for every edge if you consider vertex cover, because for vertex cover, you have to cover every edge. But for dominating set, we do not consider, we just consider for every vertex, we have to dominate it. Yeah, so it's not like we have to dominate every edge. No, okay, we only consider problem from the point of view of vertices. All right, so, but your second question is, is there an input such that the minimum dominating set is not a minimum vertex cover, right? Okay, so for example, yeah, I believe that for some graph, for example, if it's a star, right? A star is like so a star is basically a tree of depth 1. So in this graph, they have the same minimum dominating set and minimum vertex cover, right? Because you just choose the center vertex, right? So if you choose it, first of all, let's consider dominating set. So it dominates itself and all its neighbors, right? So it's a feasible dominating set. And we consider vertex cover, it covers every edge, okay? So it simultaneously dominates and covers the whole graph. Now, let's try to figure out, right, okay. So this is a case where a minimum dominating set is not an edge cover, a vertex cover, because for this triangle, if you only consider dominating set, then you can just choose one vertex, okay? But this is not a vertex cover because this edge is not covered. Okay, so I think I think a vertex cover must be a dominating set. Okay, but a dominating set is not necessarily a vertex cover. Right? Okay. OK， 还有问题吗？所以刚刚的同学有蛮不错的问题，就是 dominating set 跟 vertex cover 的关系 ，OK？ 所以有的时候最小的 dominating set 就会是最小的 vertex cover， 像这个 star。但有时候最小的 dominating set 它甚至不是 vertex cover，OK？ 它不是一个合法的 vertex cover。所以像这个 triangle 的话，你选的它就是 dominating set， 而且也是一定就是最小。但这个不会是一个合法的 vertex cover， 因为它没办法 cover 这个 edge，OK？ 那我刚刚说的是，所以从这里你就可以知道，有时候 dominating set 不会是 vertex cover， 但是我相信 vertex cover 一定就会是 dominating set。我不是很确定 ，OK？ 我们试试看。Not necessary. Okay, so I have to take that back. Okay, so sometimes a vertex cover is not a dominating set. Okay, so for example, unknown. No. Let me see. Yeah. That's right. Yeah, that's right. Yeah. So. Yeah, that's right. Okay. If you need a formal proof, it's something like this. Okay, so let's prove it by contradiction. So, suppose we have a vertex cover, which is not a dominating set. So like this one. So this one is not dominant because it is not chosen, and all of its neighbors are not chosen. But this cannot be a vertex cover because all these edges, they are not covered, right? So yeah. So if you have a vertex cover, then it must also be a dominating set. Okay, good. Yeah. So any other questions? 还有其他问题吗？那我们稍微有 delay 一点，所以我们就15分的时候再开始。OK。OK。这演算法只是就是很简单，就是你加一个很大的 weight 到每一个边，所以你加了一个很大的 weight 到边之后，你为了要去 maximize，然后我们再去跑 maximum weighted matching， 所以跟你的有点不一样，就是你会加 dummy edge， 但是这边不需要加 dummy edge， 就 edge 我都不会动，我只会把一个很大的数字加到每一个 edge weight 上面，所以因为你加了一个很大的 edge weight， 所以你如果要去 maximize total weight， 你就一定要去 maximize 你的边的个数，所以自然的这样子做出来就一定会是 maximum cardinality。
套回原本演算法的话，你不是还是要让它是 perfect matching 吗？这样还是要加 dummy edge。
哦，对，那个你可以把它想成就是第二步 maximum weighted matching 这一步，你可以先把它想成一个 black box， 就是
你是说加这个 W 大到它会大于，比如说这边是100好了，它会大于2倍的100，是这个意思？
不一定是2倍，就是这个要取决于你的几个点，但所以我说只要够大就可以。对。
OK。
我可以问一下我的算法是对的吗？
好。
就是我的算法是我先找到一个现在的最大的那个 cardinality 的 matching，
找到一个最大的 OK， 然后
我会一直找那个 augmenting path， 然后那 augmenting path 是它不会改变它的 matching 数量，可是它的权重会变大。就是它。
可是 augmenting path
应该说它
是 augmenting path 还是？
它可能是 cycle 或是 path。
所以应该是 alternating 的 path，
对 alternating，
这是 alternating 嘛？
然后它会有些条件，比如说，就是它 XOR 完之后，它不能影响到它 matching 的数量。
第一个我觉得是蛮合理的直觉。
对，因为两个 matching 的话，他们 XOR 的时候会是 cycle 或是 path。
对，所以 follow 对这样子的话，如果你手上的不是最好的，我就应该可以找到一个 alternating 的 cycle 或 alternating 的 path， 然后你替换之后 weight 会增加嘛？那要怎么找？就类似 BFS 这样去找？
对，就每个点开始做，就是你应该先从没有被 match 的点开始找，因为没有被 match 的，如果他要，就是他会有些条件，就比如说，如果我要不改变 match 数量的话，我应该要怎么找？
我觉得我乍听之下我没有想到什么太大的问题。
对，但我那时候是这样写的，但我感觉我的步骤描述可能不够清楚。
OK， 我想一下。
但 general idea 应该是这个。
对，我觉得 general idea， 我觉得应该没有什么太大问题。 可是一定会从假设我们先想 path 好了，它一定会从 unsaturated vertex 出发，也不一定嘛。
不一定，所以我有列出一些条件，就是因为为了要限制它那个 path 或那个 cycle 不能影响到它那个数量，
不能影响到什么？
不能就是你 XOR 的时候你不能影响到它的数量，就是我那时候是，
没关系，所以我不是很确定，所以。那咱们就考虑这样好了，所以假设你选了这个边跟这个边，
所以像这个需要交换的话，它就需要 cycle。所以假设，
所以找 cycle 时间复杂度不会太复杂，是不是？它会不会有太多 cycle 要找？
太多 cycle 要找。
因为假设它是一个 complete graph，那我感觉有很多可能的 cycle。
但是会满足条件的 cycle 会很多吗？
对，可是你有什么方法在一开始就类似 pruning 掉那些你不需要考虑的吗？
可是就直接从，比如说我要从这个点出发哦，那我就一直走 VFA。我觉得这有点像是那个。
可是如果这是变成一个 complete graph， 就是很大的图的话，我的直觉是有很
多个 cycle。
对，我觉得就我觉得现在的问题应该是时间复杂度的问题。
对。
我不确定这个时间复杂度会不会是爆掉的。因为它的顺序，它怎么选，然后就会有影响。
因为我那时候觉得这有点像是那个在找 flow 的时候，它不是也要找一个 path？
对，可是如果你可以把它 reduce 成 flow 的问题，我就没什么问题。但你没有 reduce 嘛？因为我的直觉是，比如说你的现在的 matching 已经有 n 个点好了，
对，
你的 cycle 可能有很多个可能要，光 cycle 就很多个可能要找。
对。
我们甚至不要管数据去了，我们就光想我们要。
单一某个点，它可以走很多方式，然后再回到这里。
不，我刚刚想的是你的 cycle， 假设你现在 matching 有 n 个点好了，
对。
那我现在要找 cycle， 假设我 cycle， 我只想要找n个。你光从 n 个点去找2/2个点出来，这边的就会让你爆掉。
对。
当然看起来你必须要每个都考虑到。
对，看起来是这样。
对，所以如果是这样的话，我觉得我可以给你部分分数，但是可能没办法跟你全对，因为题目是要 polynomial time。
对。
对。
这题的讲解是怎么做？
就加一个就加一个很大的数字到每一个 h weight 上面。然后再跑 maximum weighted 的 matching。
我是把两边的点，就是个数都全部一样，然后加到每个 h，
就是
对，再说一下
解法，对，就是老师上课讲到的解法。
可是那个就会跟你刚刚可能还没来，那就是会跟，不就这个问题，假设是这个，这样你的 output 会是什么？
对，我知道要加那个最大，是加一个大群。
那这样子会有，这样也是partial吗？
哪样是partial？
这样子。
这样子是什么意思？
应该说那个 solution 会。
那个 solution 我就觉得因为它就根本就不是正确的。我觉得正确性是一个，然后时间复杂度是一个。就我来看，你的正确性应该是，至少我没有想到什么问题啦。对但是时间复杂度那个就很明显。对。这个刚刚那个，因为刚刚有一个同学讲到类似的做法，当然就是
做出来。
我不知道，我还没改，所以我不知道。对。
没想到。
那老师是刚讲到这一题吗？
没有，我已经全部讲完。
那我可以问一下那个
dominating set
的那个它的 dual problem 是我是写说他们那个 set 里面的点不会有 common 的 neighbor。
我不太懂这句话的意思。那个 set 里面的点不会有 common 的 neighbor。
就是它的 dual problem。
嘿。
会是一个 vertex
对，也是一个 vertex set，没
然
错。
后那个 vertex set 里面的点不会 share a common 的 neighbor。
不一定吧？不一定啊，不一定啊，因为，比如说，比如说这样。那这样我就会选这个跟这个，但他们有 common neighbor，
哦，这样是可以的吗？
因为它有 dominate 所有的点。
哦，我一直它的 dual problem。
哦，的 dual problem 啊，dual problem。刚刚我们说 dual problem 是还有一点时间，就 dual problem 它的物理意义是对每一个点跟它的邻居最多只能选一个。
对，所以他们就不会 share a common neighbor 了，因为我那时候也是。
每一个点跟它邻居都最多只会选一个，就不会有 common neighbor， 是不是？
对。因为我那时候
我现在没有连得起来，每一个点，这样为什么不会有 common neighbor？ 哦，对，啊，对。
Okay, 那我这样选，因为我那时候在，因为我那时候列出来。
但不对啊。
不对吗？
不对啊。
因为我原本也是写刚老师说的那样，但我觉得好不严谨哦，所以我就。
等一下。没。像他们有 common neighbor， 你意思说这两个就不能同时选吗？
对，因为他们这样会 share 一个 common neighbor。
可是如果是 follow 刚刚的，哦，因为如果你考虑这个点，最多只能选一个。哦，对，是不是一样的？
我那时候的结论是没有 common neighbor，我列。
但是没有 common neighbor 就一定，就有两个方向啦。一个方向是，
这样好，因为如果他们有 common neighbor 的话，我把他们补集回去，那代表说会有点没有被 dominate 到，没有被 cover 到。
这应该说，我们现在看的是 dual problem 嘛？那根据 dual problem 那个 mixed integer linear program 告诉我们，它就最直觉的就是每一个点跟它邻居只能选一个。那现在看起来，如果是符合这个 dual problem， 那它确实就不会有选出来的点就不会有 common neighbor， 这个方向是没错。但如果说今天他们没有 common neighbor， 是不是就可以保证每一个点跟它邻居最后只能选一个？所以有双向。
感觉是有，因为假设我都没有 share common neighbor 的话，那我说随便挑两个点，他们一定不会是，他跟他的邻居，他跟他的邻居怎么会选？这可以反证吗？
可以啊，如果你想的话。可是，
就是如果他跟他邻居都选了，那他们就会 share common neighbor， 就对方。
OK， 我觉得不太一样，因为你来看这个图的话，我们的 dual problem 会告诉我们说，这个点跟他所有邻居只能最多选一个。然后你的是说他们选出来的点不能有 common neighbor， 但是你的定义就可以选两个点，因为这两个没有 common neighbor。
我的 neighbor 有对方。那我可能写的。
哦，你说包含自己是不是？
对。好吧，那我可能不够严谨。但就
OK， 如果是有的话，那是对，那应该是。
好了，
对，因为我的 neighbor 的定义是没有包含自己的，对。
但是我的想法中，这个是不会被我那个选到的。
对，如果那就 OK 了。对，不，对吧？反正就反正我第一个我会让助教改作业，改考卷，改完之后你们觉得有时间检查，看有没有要分数的，就你到最后再可以拿给我这样子。大概就这样子。OK， 好，会。Okay, so since we have completed the discussion for midterm, next we'll resume our discussion on the TUTE theorem, okay? And today, I will follow my notes, okay? And I believe that some of these details maybe not crystal clear, so I'm going to restate the theorem again, okay? I think I can just use the previous slide, okay? So let's first review the statement of Thieves' theorem, okay? Okay, so this notation OG is the number of odd components in the graph, okay? And the intuition behind Thieves' theorem is that, say you remove some vertices from the graph, and it generates, say, 3 odd components. So if you want to have a perfect matching in the graph, then the number of odd components cannot be too large, okay? Because for every odd component, you have to find one additional vertex to match it to get a perfect matching, okay? So the high-level idea is that the number of odd components is at most the number of vertices that you remove. And this is true no matter how you remove the vertices. So this S can be any set of vertices in the graph. So you want to remove S and see what is the number of odd components in the graph and wish that these odd components or the number of odd components is at most the number of vertices that you remove, okay? So this is Thieves' theorem. So so this is called Thieves' condition, okay? So if it is true for every possible set S, okay, then we said that this graph satisfies Thieves' condition. And Thieves' theorem says if you satisfy Thieves' condition, then the graph has a perfect matching, okay? And so the proof is by induction on the number of vertices, that is n, okay? So previously we have discussed that when n is 1 or when n is 0, the graph cannot satisfy Thieves' condition. So the smallest number of vertices, that is n, that satisfies Thieves' condition is 2. So in our induction basis, we start from n equals 2, okay? And for n equals 2, there are 2 possible graphs, okay? So the first one is just 2 isolated vertices. And the second one is 2 vertices connected by an edge. So for these two, only this one, the one that has one edge, satisfies Thieves' condition, okay? And indeed, this has a perfect matching, okay? So at least we know that when n is 2, Thieves' theorem is true because it satisfies Thieves' condition and it has a perfect matching, okay? And then we try to complete proof by induction. And so we have this hypothesis, that is, we assume that this is true when the number of vertices is less than k. And then we try to prove the case where n equals k. Okay, so next, I will do the proof again. Okay. So recall the high-level idea is to find a spatial vertex set. Okay, so let me write down the property for this spatial set. Okay, so we have 4 spatial properties. Okay. So first of all, I assume the size of this set C is H. So there are H vertices in the set C. Okay. So the first property says, after you remove this set C from the graph, you'll get some odd components. So the number of odd components is just the size of C. So in this case, because we've just assumed that the size of C is H, so this equals H. Okay? So this is the first property. And the second property is that actually after you remove C from the graph, all components are odd. Okay? So there's no even component. And the third property is let G1, G2 up to GH be the odd components. Okay, so we know that this must be odd components by the first 2 properties. So we use G1, G2 up to GH to denote the odd components after we remove C from the graph. Then for every this component Gi and every vertex V in Gi, we can remove this vertex V from Gi, then the remaining graph still satisfies Thieves condition. Okay? And the next one says, once again, for every component Gi, so these are the components we get after removing C from the graph. So for every component Gi, there's a spatial vertex. Okay, so I want to stress that for the third property, this is true for every vertex V, okay? But for the last one, this is true only for some vertex Vi, okay? And so the special property about this Vi is that you can match this V1, V2 up to VH with C in the original graph G, okay? So we've explained the reason that this set C implies the whole proof. The reason is that, so you have a set C, say 5 vertices. Okay, so the first property says the number of components or the number of odd components after you remove this set C from the graph is exactly the size of C. So in this example, we have 5 vertices in C, so we have 5 odd components. So all these components, G1, G2, they are all odd components. And yeah, and because all the components are odd, we do not have even components here. Okay, so next, the third property says for every vertex V, so after you remove V from, say, G1, okay, yeah. So after you remove V from the graph, G1, the remaining graph still satisfies Thie's condition. Okay. So this satisfies Thie's condition. So by the induction hypothesis, so what is the induction hypothesis? Okay, so assume that Thie's theorem holds for smaller graph actually. Okay, so clearly this rate graph is smaller than the original graph. So by induction hypothesis, if it satisfies Thie's condition, then it has a perfect matching. Okay, and this is true for all the other components. Okay. So intuitively, we use this third property to create a large matching. Okay, so it does not saturate all the vertices, but most of the vertices in the graph, they can be saturated using the induction hypothesis. Okay. Okay. And so for the last property, it says there's a spatial vertex vi in every component such that there's a perfect matching between these spatial vertices and the vertex set C. Okay? So I think logically we first apply the last property. Okay? So we first find a perfect matching between C and GI. Okay? So we first find these bridges between C and GI. So we can first identify these spatial vertices. And then we remove it from the component and then use the induction hypothesis to find a perfect matching for every component here. Okay?好，所以再讲一次，刚刚最关键的事情就是刚刚这个，我觉得应该是逻辑上应该是第4步先了 ，OK？ 所以就是每一个这里的 R component， 我都可以帮它找到一个特殊的 vertex。那这个特殊的 vertex 刚好可以跟我们找到这个 set C 有一个 perfect matching，OK？ 那所以剩下的就会是除了这个特殊的 vertex 之外，其他的点要怎么 saturate？ 那其他的这边，因为你把 V 拿掉之后，剩下的刚刚的第3个 property 就会跟你讲说，这个每一个它都会满足 Two's condition。所以根据 induction hypothesis， 我们就可以知道这些，因为它有 Two's condition， 所以它就有 perfect matching。Okay, so so basically this is what we're going to prove next. That is, we can find a vertex C that satisfies all these 4 properties. So let's first give the construction of C. Okay. And the construction is quite easy, okay? So we first consider the first property, that is the size of C equals the number of R components after you remove it from the graph. So there are multiple sets that satisfies this condition. So we want just the largest one, okay? So for example, we've discussed that one way to create a set that satisfies the first property is to pick any non-cut vertex, okay? So what is a cut vertex? A cut vertex is a vertex such that after you remove it from the graph, you increase the number of components, okay? It's like you disconnect some component if it is a cut vertex. So a non-cut vertex is a vertex that after you remove it from the graph, you do not disconnect any component, okay? So if you remove a non-cut vertex from the graph, well, then the size of C is 1, okay? And because all the components are even if you satisfy Two's condition, so if you remove one vertex from an even component, you get one odd component. Okay? So this just shows that at least we know some vertex set satisfies property 1. Okay? But in this construction, we want to find the largest one. Okay? Okay? And because this is just a proof, we don't need to give like a constructive proof. We don't need to give an algorithm to find such a set. We just assume that C is the largest set that satisfies property 1. So this is how we construct C, okay? So clearly, the construction satisfies property 1, okay? And next, let's prove property 2. Okay? So what is property 2? So property 2 says, after you remove C from the graph, all components are odd. Okay? So let's prove it by contradiction. So for the sake of contradiction, let's assume that some component is even. Let's call this component G prime, okay? Okay, and then we need to find a contradiction. So the idea is that if you have an even component, then once again you can find a non-cut vertex from that even component and add that non-cut vertex to the set C. And then you get a larger set C, okay? Okay. So yeah. So if you have an even component, you can just add some non-cut vertex to the set C. Then it's easy to see that this new set C also satisfies the first property, okay? Because this even component, G prime, after you remove one vertex, it becomes an odd component. So the number of odd components is increased by 1. And similarly, the size of C is increased by 1. Okay? So, yeah, so this new set also satisfies property 1. But this is a contradiction because we just assume the set C is the largest one that satisfies property 1. So this cannot happen. Okay? So this is proof of property 2. So next, proof of property 3. Okay. So recall that property 3 says for every odd component Gi and every vertex V in that odd component, Gi minus V. So this is the graph obtained by removing V from the graph Gi, okay? So this remaining graph also satisfies Thieves' condition. Okay, so once again, we prove it by contradiction. Okay, so what is like the negation of the statement? Because if we want to prove it by contradiction, we have to first find the negation of this one, okay? So the negation would be there is some component Gi and some vertex V in the component Gi, such that Gi minus V does not satisfy Thieves' condition. Okay. Okay, so what does it mean if some graph does not satisfy Thieves' condition? So what is Thieves' condition? Okay, so this is Thieves' condition. Okay, so if a graph does not satisfy Thieves' condition, this means there is some set S such that the size of S is, the number of odd components after you remove S from the graph is greater than the number of, the size of S. That is, the number of odd components is too high, okay? Because if you want to have a perfect matching, you do not want many odd components. So if it violates Thieves' condition, it means you have a lot of odd components after you remove some vertex set S, okay? Okay. So this is the number of odd components after you remove S from the graph. And since we assume that this does not satisfy Thieves' condition, this number will be very large so that this is greater than the size of S. Okay. Okay, so this is the assumption we get if we try to prove it by contradiction. Okay, so next we're going to find a contradiction. Okay, So I claim that this C is the set C we've got previously, and this is V, this vertex V, and this is S, so this set S, okay? So I claim that this new set satisfies the first property, and this will create a contradiction, okay? So why is this a contradiction? Because we just claimed C is the largest one that satisfies property 1. But now you have a larger set that satisfies property 1. So this is a contradiction, contradicting to the assumption that C is the largest one. Okay? So if we have the claim, then we have the proof of property 3. So next we're going to prove this claim. Okay? Okay, maybe before I proceed to the proof, 我稍微 summarize 一下我们现在手上的资讯 ，OK？ 所以我们接下来要做的是要去证明第三个 property。第三个 property 就是每一个这个 odd component， 这里的 odd component 就是你把 C 拿掉之后 ，OK？ 的剩下的 component， 就这些都会是 odd component。那这边的重点是，不管你今天看的是哪一个 R component， 然后不管你看的是这个 component 的哪一个 vertex V， 你把它拿掉之后，它都一样会满足 Tooth condition。OK， 这个就是我们之前，在哪里？这里 OK， 我们之所以会刚刚第三个 property 就是要去说里面这些 R components 里面这个红色的圆圈圈，它们里面会有 perfect matching。那我们刚刚说要有 perfect matching 很简单，你只要说它有 Tooth condition 就可以。OK， 所以这里的 V 就是我们刚刚那个 V。OK， 所以这个 V 可以是任何一个 vertex。你把它拿掉之后，它会满足 Tooth condition。这个是我们想要证明。那我们刚刚说你要说明某一个 graph， 在这边就是这个红色的这个。你把它本来的拿掉 V 之后，剩下的那一个就这个，它满足 Tooth condition 就代表说，不管你在这个 graph 拿掉什么点，拿掉哪一些点，剩下的 R components 的个数都不可能太多，因为太多你就会爆掉，你就不会有 perfect matching。所以换句话说，如果不满足 Tooth condition， 就代表说这个红色的这个 graph 里面，你可以找到某一个特别的 set S。你把它拿掉之后，会产生一大堆的 R components，OK？ 那这个就代表它违反 Tooth condition。所以我们刚刚说我们要去用反证法去证 property 3， 那就代表说我可以有一个 component GI， 还有某一个 vertex V， 那这个 GI 减掉 V， 就是你把 V 从 GI 拿掉之后，它不会满足 Tooth condition。那我刚刚说它不会满足 Tooth condition， 就代表说它有一个特别的 set S。那多特别呢？就是你把它拿掉，会有很多的 R components。这边的很多的 R components 代表说它的 components 比 S 的 size 还要更大。OK， 那接下来我们就要想办法找到矛盾，因为我们要反证法嘛，这就是反证法的假设。所以接下来我们就要看矛盾在哪里。所以矛盾就会是我们底下这个 claim， 这个 claim 是说，如果真的你有找到这种 S， 这么特别的 S， 那你事实上就可以找到一个更大的 C。OK， 这更大的 C 怎么得到？就是 C 再加 V 再加 S， 它就会是一个更大的 set， 然后它会满足 property 1。OK， OK， 所以接下来我们就要去看这个 claim。为什么是对的？ OK， 所以我们接下来要说的就是它这个你把这里的 C 换成刚刚那更大的 set， 一样会满足。OK， 所以我稍微写一下。Okay, so this is property 1. Okay, property 1 says there's a set C such that the size of C equals the number of odd components after you remove the set from the graph. So in this claim, the set we are considering is this set, C union V union S. So the size of C union V union S equals the number of odd components after you remove this set from the graph. So we want to prove this is true, okay? So this is our goal. Okay. Okay, because I recall that the statement of Thieus' theorem says the graph satisfies Thieus' condition. Okay. So we have okay. So Thieus' condition says no matter which vertex you remove from the graph, the number of odd components cannot be too high. So it is at most the size of the set that you remove. Okay? So we have this inequality because the whole graph satisfies Thieus' condition. Okay? And because we have an equality here, so we have to prove the other direction. That is, I want to prove this direction. Okay. Okay, so after we have these two inequalities, we have achieved our goal, which finishes the proof of property 3. Okay. So let's try to simplify this a little bit. Okay, so what is this size? Okay, because we've assumed the size of C is H. So this is just H plus 1 plus the size of S. Okay? So how about the right-hand side? Okay. So this is the set C, sorry, this is a set S, and this is the vertex V, and this is C. So the right-hand side, okay, is the number of arc components after you remove C union V union S. So in this particular instance, the right-hand side will be four plus 3, okay? So how do we get this 4 plus 3? So what is 4? So this is just h minus 1. So why do we have this minus 1? Because we exclude this graph, or sorry, this component. So we have this minus 1. All right? And why do we have this h? H is the size of C, which is also the number of arc components here. So so by decreasing 1, we get the number of the number of arc components here. Okay, and this is the number of arc components after you remove V and S from the component GI. Okay. All right. So the right-hand side is h minus 1 plus the number of arc components you get after you remove S and V from the component GI. Okay. So you can cancel out this H and change this minus 1 to the left-hand side. So rearranging these terms, we get S plus 2 is at most the number of arc components after you remove V and S from GI. Okay, so this is our goal. Right, so we're almost there, so I want to finish the proof, and we take a 10-minute break, okay? Okay, so recall that we have this assumption. Okay, so these are just the two terms we have in the right-hand side and the left-hand side. Okay, so let me just copy this. So once again, the high-level idea says you have lots of arc components. Okay, the number of arc components is greater than the size of S. So this is the assumption we have due to because we want to prove it by contradiction. Okay. Okay, so we already have this inequality. So it's very close, okay? So the right-hand side is greater than the left-hand side. But here I want to further show that the difference is at least 2, okay? So perhaps in this case, they only differ by 1, okay? Then it is not enough. So I want to show that the difference is at least 2, okay? So since we already know that the number of arc components is greater than the size of S, you want to further prove this, you only need to show that they have the same parity. That is, if this is even, then this is even. If this is odd, then this is odd, okay? So if they have the same parity, then their difference is at least 2, okay? Okay. Okay, one last step. So S Okay, so if S is even, then I claim that this set is also even. So why? Because GI is an odd component, and you remove one vertex from it, and since S is even, so you remove one from an odd component, you get an even component, and then you remove even number of vertices from an even component, once again you get an even component. So this is even. So if this is even, then the number of components or the number of odd components is also even because you have an even number of vertices, so the number of odd components must be even. Okay. Right, so this is one case. Okay, so here we can see that S is even, and this number of odd components is also even. Now, if S is odd, then if you remove one vertex from an odd component, once again you have an even component. Okay, and you remove an odd number of vertices from an even graph. Okay, then you get an odd number of vertices. Okay, and since the number of vertices is odd, then the number of odd components must be also odd. Okay, and that's it. That's the proof for property 3. Okay. 我很快summarize 一下，然后我们再休息一下。OK， 所以刚刚这个 proof 是最复杂的一个步骤。等一下那个 property for 的 proof 也很简单。OK， 所以最困难的就是这个。所以我们要做的事情就是刚刚我讲的就是要去说这个 claim 是对的。OK， 这个 claim 就是你可以找到一个更大的 set C 去满足第一个 property。那这个第一个 property 如果满足，就代表这个 set 的大小跟你把这个 set 拿掉之后的 R components 的个数会是一样的。OK， 所以这就是我们刚刚的目标。OK， 所以这是一个等式。所以如果你要证明一个等式，你就剩小于等于跟大于等于，就这两个。OK， 那上面第一个这个它为什么是对的？因为整个 graph 它满足 Two's condition， 那就代表说整个 graph 里面，你不管挑哪一个 set， 你把它拿掉之后 ，R components 的个数一定不会太多。OK， 这是 Two's condition 它的直觉。OK， 所以这边 R components 的个数就不会超过这个 set。OK， 所以这是一个方向。所以剩下就是要去看这个另外一个方向。OK。然后在做另外一个方向的时候，我们先做一个化简，就是左边跟右边，左边的比较简单，就是 C 的大小就是 H， 然后 Union 一个 vertex， 所以它大小就是1，然后这边就只是 S 的大小。因为 C 跟 V 跟 S 它们都是 disjoint， 所以它们的大小连起的大小就是各自的大小加起来。OK， 然后这一个左边的这个右边的这个 R components 的个数就会是。先看一下，他这边做的事情是，你把本来的那个 C 拿掉之余，又再拿掉了 V 跟 S， 然后我想要看掉多拿了这两个 vertex 之后，我会有哪一些 R components。那我刚刚说的，就是你把 C 拿掉，然后再拿掉 V 跟 S 之后，你产生的 R components 的个数，就本来的那一些，那 H 个，我们就先把这个扣掉。对，扣掉1，所以就是这个上面这4个，然后有可能会有一些新产生出来，就是上面这3个，我这边画的就是你把 V 跟 S 拿掉之后，这个 GI 它剩下的 R components 的个数 ，OK， 所以这个就会是上面这边，那这里这两个 H 就可以消掉，然后你把这个-1移项，你就可以得到这个，所以这就是我们新的目标。你只要证明这个，就可以证明上面这个。OK， 所以这边只是再写一次。那我们刚刚的反证法有一个假设是，这个是我们反证法的假设，就是你可以找到一个很特别的 S， 那这个 S 拿掉之后，你会有很多的 R components。OK。所以我这边只是原封不动把它抄过来，只是稍微换一下方向 ，OK。好，所以你会看到这两个已经很接近了，就是右边都是一样的，左边差2 ，OK。事实上，如果你想要的话，你也可以把这个写成这样子，因为这两边都是整数，所以如果大于的话，就代表它至少是大于等于1这样子 ，OK。所以这样可能会搞不好会更容易看出这两个的差别。这两个差别就是只差1而已 ，OK。所以你要怎么说这两个它不是只差1，它事实上差到2。你可以去说左右两边就是这个 S 跟这个 R components 的个数，事实上它们要么都是偶数，要么都是奇数 ，OK。所以要怎么看说它们要么都是偶数，要么都是奇数？就我们先考虑的是就是 S 是 even 是偶数的情况下。所以我们先来看，就是这个 GI 跟 V 跟 S， 我不是直接去看这个，我是先去看一下它的大小。那它的大小，因为 GI 就会是 odd， 这个是我们之前的property 有看到的。然后你删掉一个点，所以就扣一个，然后再扣掉 S。那 S 如果是 even 的话，就是奇数扣掉1就变偶数，偶数再扣掉偶数，一样会是偶数。那如果你所有的点的个数是偶数，那奇数 component R component 的个数就一定也会是偶数 ，OK？ 那另外一个方向也是一样 所以这个 proof 就会是这样子。OK， 好，所以我们就休息。这个刚刚比较累一些，所以我们就休息到25分。那我们等下再回来看第4个 property。可以，你可以自己翻，对。有问题吗？你要看，因为这个是之前写的，对。
是我有点 lost in track。
OK。
它到底是在我们想要证明的应该是 G 是符合 Tooth conclusion 是吧？我应该是假设，就它是假设 n 小于 k 是要符合 Tooth conclusion，所以
不是。好，那
说这样子，这边就是 property 3这边。
对。
这个为什么需要证？这不是那个 induction 假设吗？就是
了解，我大概知道你的问题。OK， 所以这边的关键是这样，就是要先回来看一下整个 Tooth theorem。OK， 他这边说的事情是，如果你满足 Tooth condition， 你就有 perfect matching， 这是我们想要证的。所以这个前面的这里的 induction， 这个他说的就是，如果你现在的 graph 的点的个数是小于某一个数字 k 好了，那你接下来，就是我们的 hypothesis 就跟你讲说，这样你就会有 perfect matching。那我们接下来要说的是，那如果我今天的这个 graph 再更大一些，而且它也满足 Tooth condition， 那它会不会有 perfect matching？
n 小于 k 和 n 等于 k 都满足 Tooth condition， 然后
对，
这个还没有证它符合 perfect matching。
对，对。
那第一步这边呢？第一步这边 proof of the property y， 这个
对，
这边是就是这边 largest set， 可是要怎么知道它是有的？因为
OK
好像是直接说它
OK， 所以这边就我刚刚说的这里的 proof， 它比较像是一个存在性的 proof。那
可是你假设它有，
对，可是我为什么可以假设它有？就因为我这边至少给你一个这个键法，当然这个不一定是最大的。所以当我不管你怎么找到最大，就是当我至少告诉你会有一个。有了这一个之后，你就可以就是我们就可以假设它是最大的，就对。OK， 可以跟我讲一下你刚刚卡住的点。
我刚刚在就是因为跳来就要证明的目标一直在变嘛，
是是是，
我从公司这边，我错这边就是错最大的、这边，就是我以为是要证明说这个是这是满足 tools condition，然后
对
这个不满足，还不知道能不满足，想要证明这个是满足 tools condition。
了解了解，好好好好
这，点确认完之后，就整个就大跃进，就是了解很多，
了解了解
确认一下 priority one 之后，整个就接起来。
OK 好
我当，时就是卡在第三点啊，我刚刚就卡在这边说，第三点这边说，我卡在这边说，为什么这边是要写那个，就是还要再去证明什么它不满足 tools condition 那些，我想说不是应该是所有小于 k 的 graph 都要是满足 tools condition，我就很疑惑。
好，了解了解
现在就完全听懂。
，OK，好。 Okay, so next, let's move on to the proof of property 4. Okay. So first, let's recall property 4 says for every component, there's a spatial vertex Vi, and we need to find such a spatial vertex Vi, such that there's a perfect matching between the set C and V1, V2 up to VH. Okay. Okay, so in order to find this perfect matching between the R components and C, we will create a new bipartite graph, okay? And because for bipartite graph, we can use Hall's theorem to prove the existence of perfect matching. So we're going to create a bipartite graph. So in this bipartite graph, the two parallel sets are C, so this is just the set C, we've considered previously, and the other parallel set is X. Okay, so next I'm going to give you the definition of X. Okay. So basically, for every R component, Gi, we create a vertex Xi in this capital X. Okay? So these are the two parallel sets. And for the H set, okay? So we will create an edge whenever the R component is adjacent to some vertex in C. So let me give you an example. Okay. Okay, so here I draw more edges between the R components and C. And I want to stress that, for example, in G2, the two endpoints here are not necessarily the same vertex. Okay, so these two endpoints can be different vertices. Okay, so similarly for these three endpoints, which are the endpoints of bridges between G3 and C, these three endpoints can be different vertices. All right, so according to the construction, we have 5 vertices in X and 5 vertices in C, because the size of C here is 5, okay? And how do we add edges between X and C? So first, let's consider G1. So G1 is adjacent to, according to this graph, it is adjacent to C1. So this is C1, C2 to C5. So it is adjacent to C1 and C2. So we just add an edge between x1 and c1 and x2 and c2. So similarly for x2, since G2 is adjacent to C2 and C3, we'll add an edge between these two sets. Okay. Okay. And for G3, it is adjacent to C1 and C3 and C4. Okay. And for G4, it is adjacent to C4 and C5. And finally, for G5, it is adjacent to C5. Okay, so this is how we create the new bipartite graph B. Okay, so basically we use the we use the edges between C and the arc components to create the bipartite graph. Okay. Okay, so next, I think it's clear to see that if there's a perfect matching in this bipartite graph, then there's a perfect matching that satisfies property 4. Okay? So all we need to prove next is to show that B, so our goal is to show that B has a perfect matching. Okay, and this perfect matching also tells you this spatial vertices V1 up to VH. For example, in this bipartite graph, I think this is one perfect matching. Okay, so this perfect matching says for G1, the spatial vertex V1 should be the one that is adjacent to C1. So in this case, this guy. Okay, and for G2, the spatial vertex V2 should be the one that is adjacent to C2. Okay, so this guy. Okay, and so on. So really, this perfect matching also gives you this spatial vertices Vi. Okay. Right. So anyway, our goal is to prove the existence of perfect matching in B. Okay. So to prove this, we'll use Hall's theorem. Okay. So let me first recall Hall's theorem. Okay, so what is Hall's theorem about? So in Hall's theorem, again, you consider all possible subsets, but this time just for X, okay, or any parallel set. And you want to make sure that the number of neighbors of the set you choose is greater than or equal to the size of the set, okay? So applying to this context, we want to show that Okay. So our goal is to show that for every possible subset S, the size of S is amongst the number of neighbors of S. So if this is true, then Hall's theorem says this graph, well, it says this graph has a matching that saturates X. But in this time, because B in this bipolar graph, B, X, and C, they have the same size. So if you can saturate X, and you can also saturate C. In other words, this is a perfect matching. Okay? Okay, so this is what we're going to prove next, and this one is easy. Okay? So once again, we prove this by contradiction. So we assume for the sake of contradiction, there is a set such that the size of the set is greater than the number of its neighbors. Okay? And I want to stress that this neighbor set is a subset of C, okay? Because say you can consider this one, okay? So this is, say, S, okay? Then their neighbors clearly is a subset of C, okay? Okay, but visually we have a large set S and a small set N S. Okay? Or okay, so in this example, we consider this set S. So these are the corresponding vertices for G1, G2, and G3. So their neighbors are just C1 and C2. Okay? So you can see that here S is larger than NS. Okay? So there are 3 vertices in S, while for NS, there are just 2. Okay? And we want to find some contradiction. Okay? So this really is the last statement of the whole proof. So where's the contradiction?可以 C 里面的这可能可以有边，可以没有边都可以，对，不一定要是 isolated， 不需要。所以我再整理一下 ，OK， 我看一下我的笔，确定一下 ，OK， 我接下来真的就只需要再就一句话，整个 proof 就结束了 ，OK。我说的整个是整个 Thus theorem 的 proof，OK， 从 induction 到 property 1、2、3、4，这全部就是这里。接下来我要写的就是最后一句话。那在讲这最后一句话之前，我想要再稍微 summarize 一下我们现在做的事情 ，OK。我们要做的是它会满足 property 4，OK。所以我们刚刚做的事情是我们去建了一个 bipolar graph， 然后 这个 x 跟 c 我们刚才已经解释过，还有包括它们的 edge 怎么相邻的 ，OK。所以我们想要说的是，这个 bipolar graph 它有一个 perfect matching， 因为我们刚刚说了，如果这个 bipolar graph 有 perfect matching， 那就像前面这个 example show 的，如果你有 perfect matching， 你就可以回推知道说，这个每一个 GI 它的那个 spatial vertex 应该要选哪一个 ，OK。所以我们接着要去看，为什么它一定会有 perfect matching？OK， 所以我们之前上课期中考前有讲过 Hall's theorem，OK，Hall's theorem 它说的事情就是，你去看这个 x 随便一个 subset， 它的邻居一定要是，如果它邻居很多个，那代表你很容易 match， 很容易去 match 这个 s。那如果这个是对所有的这个 subset s 都满足，那就直觉上来讲，它就会有 perfect matching， 因为不管你的这个 s 怎么选，你都很容易去 match 这个 s， 因为它有很多个邻居 ，OK。所以这样子它就有 perfect matching， 这个确实刚刚这个直觉是对的，就是 Hall's theorem 说的。所以我们要说的事情就是，真的要去看，这句话为什么是对的？为什么你在这个 x 里面，不管你随便选哪几个 component， 那他们的邻居就一定都会有很多个 ，OK？ 为什么这句话是对的？那我们这边是反证法，所以我们假设，这是错的，所以真的可以找到一个 x。的 subset， 所以像这边的话就是 x1、x2 跟 x3， 还有我们发现这个 x1、x2、x3 它们的共同的邻居很少，我刚没不是共同邻居，是他们的邻居 ，OK， 不一定要共同 ，OK， 所以他们的邻居的个数，像这个例子只有2个，所以它就这个就是一个因为我们要反证法嘛，所以就是假设它没有满足上面这个 ，OK， 没有满足上面这个。就代表它真的有这个 s， 然后它的邻居很少。那我们最后就只差一句话，就是要看出来到底矛盾在哪里。OK， 我可以给大家一个 hint， 这个 hint 是也顺便回应到刚刚下课有同学来问 ，OK， 就是说我们整个 theorem 要证明的事情是。如果这整个 graph 它满足 Tooth condition， 就是这个 R components 的个数一定不会太多的这个 condition， 只要你满足它，你就有 perfect matching。所以我们的假设是，这个 graph 它是有满足这个的，它是有满足 Tooth condition。那在这个情况下，我们要去说它有 perfect matching。好，所以最后再回来这里。所以换句话说，我们这边我们的假设就是它是有满足 Tooth condition。那我要说的是，这张图上面有一个矛盾，就是它事实上不会满足 Tooth condition。所以问题是它哪里不满足 Tooth condition？ 没错，就这样子 ，OK。所以这里的矛盾就是，如果你今天选的就是 C1 跟 C2， 那你把它拿掉之后，会有几个 R component， 至少就会有这3个 ，OK。那所以这 R component 就太多了，就会超过你拿掉的，所以这就违反了 Tooth condition， 所以就结束。OK， 所以我们就是把这刚是这个例子啊，如果是变成 proof 的话，就是很简单，就是我们刚才已经说了，你有这个 s， 然后它的邻居很少，所以你就把这个邻居拿掉，所以这就对应到这个例子，就是把这2个拿掉。那你拿掉之后， 你就至少会有S 个这么多个 R components， 而且这边是至少。OK， 那因为这个 R components 很多，会比你拿掉的更多，所以它就违反 Two's condition。所以这就矛盾了，因为我们是假设这整个 graph 是有满足 Two's condition。OK， 好，所以这个就是最后整个 proof。好，所以因为只剩不到15分钟，我也没办法讲新的 ，OK， 所以我们就再稍微整理一下我们今天刚刚看到的这个 proof，OK， 所以我觉得最逻辑上一个很关键的事情就是你要知道你现在的假设是什么，然后你要知道你的目标是什么。所以对 Two's theorem 来讲，你的假设就是你不管拿哪一个 set。拿掉之后 ，R components 的个数都不能太多，这就是你的假设。那更精准一点去讲，就是不会太多，指的就是它不会超过你拿掉的那个 set 的大小。OK， 那如果这个是对，不管你怎么拿，刚刚那个都会成立，那我们就会说这个 graph 是满足 Two's condition。OK， 那这个是我们的假设。OK， 所以其实光假设就有一点复杂。但是我们真的要证的事情是说，如果你有这个假设，那你就一定会有 perfect matching，OK？ 所以这个是整个要去说明的事情。所以上面这个是你已知的，你要根据这个资讯去找到一个 perfect matching。好，那所以刚刚的这个 proof，特别是 induction 的部分。它就会是说，这是 hypothesis，OK， 所以我写一下。所以就是数学归纳法 ，OK， 数学归纳法我们假设，刚刚那个 statement 它只要是小于 k 的时候，就节点个数是小于 k 的时候，都会成立。那我们接着就要证，当节点个数是 k 的时候，也会成立。那这句话的意思是什么？就是如果你今天这个 graph 是有 k 个点，而且这个 graph 满足 Two's condition， 在这两个情况下，你要去证明它有 perfect matching，OK？OK， 所以后面这边你在想的时候，你心中要有的假设就是这整个 graph 它是满足 Two's condition， 这整个 graph 不管你怎么拿，你的 R components 都不会太多，所以这是整个 graph，OK？ 所以我们在这整个 proof 里面有一些比较 tricky 的地方，就是特别就是第3步这里，这个你说整个 graph 有满足 Two's condition， 那一部分的 graph， 一个 subgraph 会不会一定满足 Two's condition？ 不一定。OK， 因为你整个 graph 有 perfect matching， 那不代表你随便挑一个 subgraph， 它都会有 perfect matching， 这是不一定的。所以这个你就需要真的去证明说，就连这个 subgraph 它也会满足 Two's condition。那因为这个 subgraph 比较小，所以我们就可以用刚刚的 induction 的 hypothesis 去说明说，我们之前已经说了，我们假设如果 graph 比较小的时候，而且它满足 Two's condition， 它就有 perfect matching。OK， 然后最后面就是 直接就有用到说我们整个 graph 是有满足 Two's condition，OK，、所以去读一个 proof 的时候，你永远都可以去找 OK 这个 proof 的这个应该说我们要去证明的那个 statement 那个假设有没有用到，它用在哪里。所以从我们加马后炮来看一下，我们可以来整理一下整个 graph 它满足 Two's condition 这一个假设我们用在哪里 ？OK。我会说这里其实也有用到，就是说这个就是你把一个 non-cut 的 vertex， 就光选那个 non-cut 的 vertex， 它就会是一个满足 property 1的集合。这一个其实它隐含的就有用到整个 graph 是有满足 Two's condition。为什么？因为如果一个 graph 它满足 Two's condition， 所有的 components 就会是 even components。那在 even component 里面，你拿掉一个 non-cut 的 vertex， 它就会变成 odd。所以这个事实上，我虽然说我没有写，但它其实隐含的还是有用到 Two's condition， 就是整个 graph 满足 Two's condition。OK， 然后这一个这个就没有。OK， 这个就是很单纯的，就是如果你有一个 even 的，你把它拿掉，那就对。这边我们这时候可以假设它有一个 even 的，所以我们要用反证法。OK， 那 property 3也有用到整个 graph 是满足 Two's condition 的，是在这里。OK， 这个我就明确写出来。所以因为整个 graph 它要满足 Two's condition， 所以不管你今天挑哪一个 set。拿掉之后，它的 R components 的个数都不可能太多 ，OK， 所以这里我们也有用到。那第4步就更不用说，所以如果马后炮来看的话，整个 graph 满足 Two's condition 这个假设我们在 property 1、property 3、property 4都有用到 ，OK。然后另外一个我们有的假设是 induction 的 hypothesis， 不过这个我们刚才已经有讲到了，所以我们在那里用到 induction 的 hypothesis， 就是这每一个比较小的 graph， 就是你把那个 spatial 的 vertex 删掉之后，剩下的那一个，它满足 Two's condition。所以在这边我们就可以用 induction 的 hypothesis 去说明说，因为它满足 Two's condition， 所以它有 perfect matching。OK， 所以整个 property 1、2、3、4其实没有用到 induction 的 hypothesis， 唯一会用到 induction hypothesis 的地方，其实是在有了这个 statement， 这个 C。的特性之后，要怎么去说明 n 等于 k 的也会成立？事实上是用在这里 ，OK， 就是这些小的红色的 component， 它有 Two's condition， 所以它有 perfect matching，OK。好，所以这是一个，这应该是我们这学期看到就是最庞大的一个 proof， 所以大家可以去从不同角度去看一下这个 proof，OK。好，所以我想，我不知道大家有没有什么问题。OK， 如果没有的话，那我们今天就上到这里。哦，好，没关系。可以啊，可以啊，可以。